Hello everyone, I'm Zisu from the Hong Kong University of Science and Technology. Today I want to present my work enabling voice-accompanying hand-to-face gesture recognition with cross-device sensing. This work was conducted in the Pervasive Human-Computer Interaction Laboratory at Tsinghua University and was collaborated with HKUST Apex Lab. What is a voice-accompanying hand-to-face gesture? From linguistic research, people tend to perform multi-modalities like facial expressions, body movements, and gesture with speech simultaneously to express emotions. And these gestures are mostly performed by hands near the speaker's face, which is defined as hand-to-face. Hand-to-face gestures are proven to be natural, expressive, and more related to the speech by the existing research. We could find example VAHF gestures in emojis like the picture shows. These gestures are all performed by hands near or on the face, and people tend to perform these gestures in conversation to express some emotions or narratives. The paper is about exploring and recognizing voice-accompanying hand-to-face gestures by cross-device sensing. The main contribution of our work was to conduct a comprehensive study for the VAHF gesture set, and then we proposed a sensor fusion technique for recognizing it. Lastly, we present some use cases for VAHF applications. Our work was really motivated by the following observation and prior research problem. Voice input has become a natural and always available interaction modality for wearable devices, such as earphones and smartwatches. However, the modality control, for example, the wake-up state, the selection of the target device in voice interaction is still a challenging problem due to the implicitness of modality information in speech and restricted NLP techniques. In this case, as figure 1 shows, people have to repeat the hot words like "Hey Siri" to wake up the device or enable multiple rounds of dialogues. We can look at the example from the prior work. Yang and all used a simple hand-on-mouse gesture to replace wake-up words in voice interaction. And this gesture is more accessible than a physical or software button, especially when the device is not in the user's hands. So our motivation is to enable recognizing hand-to-face gestures to remove the extra burdens of modality control and implemented it for voice interaction on wearable devices. In our observation session for the firstly, we asked our participants to brainstorm VAHF gestures as many as possible, regardless of application scenarios or tasks. And we got 15 VAHF gestures in this process. And then we conducted the subjective evaluation on 7 points like the scale questionnaire on usability, social acceptance, disambiguity, and fatigue. This is our results of subjective evaluation. The highlighted 8 gestures were results after our optimization process. To make our gesture set representative and easy to use, we optimized our subjective results by the following principle. We categorized the gestures with 3 morphology features, which are the contact position, the contact type, and the occlusion state, as these gestures could yield the same sound propagation path and potentially have similar semantics with application scenarios. For example, as the picture shows, this gesture's contact position is the mouth and the cheek. Its contact type is the palm, and the occlusion state in the propagation path from the mouth to the ear is partially occluded. This table shows the categorized results of the 3 dimensions. We chose one gesture from each category with the highest subjective scores for our final gesture set. For example, we found 4 gestures all belong to EFH gestures, which are similar in morphology and easy to cause ambiguity when used. So we chose gesture 1 to our gesture set. As we optimized the initial results, we got 8 VAHF gestures with 1 empty gesture as our finalized gesture set. After finalizing the gesture set, we thought to find out efficient hardware forms and algorithms to recognize these gestures. So the first question we need to think about is what types of features would VAHF gestures yield? Here we summarize some of the key features that make VAHF gestures distinguishable. The main category of gestures we observed is that hand-to-face gestures would influence sound propagation to different microphone channels, making differences in amplitude, phase, and the frequency response. Taking this gesture, holding up the hand beside the mouth as an example, the sound propagation path to the right earbud was blocked by the holding up hand, leading to difference in amplitude and frequency response. Also, the microphone positions of a specific gesture brings a unique phase difference. After category of features is that the hand position, attitude, and movements, which can be potentially detected by wearable devices. Taking these considerations, the design goal of our recognition system is to sense VAHF gestures with distributed sensor nodes by observing channel differences. We chose 3 types of commodity devices as sensor nodes, a pair of ANC earbuds. Each earbud has 1 feed-forward microphone and 1 feedback microphone, a smartwatch with 1 microphone and 1 speaker, a smart ring with 1 microphone and 1 IMU. In total, there are 6 microphones, 1 speaker, and 1 IMU in our sensing system. Here is our hardware prototype. We used a Zoom H6 recorder as the audio card to collect these 6 channels of audio input. To create more precise features indicating phase difference, we let the speaker play ultrasonic sharp signals in loops. All the audio data and IMU data are streamed to a Python backend synchronously. This figure shows an overview of our algorithms, consisting of 3 submodels: the vocal model, the ultrasound model, and the IMU model. For more details of each channel, please refer to our paper. For the evaluation, we collected audio samples from users and performed leave one out cross-validation on dataset. We enhanced the data by randomly cropping and shifting the original audio samples. We conducted 3 evaluation tasks, 2 factorial evaluation on device combination and model selection, an evaluation on a reduced gesture set, and an ablation study. This table shows the results of the 2 factorial evaluation. The levels are listed below the table. From the table, we can figure out that the fusion model achieved the highest accuracy of 91.5% for the 9-class classification. The accuracies are constantly improved by bringing more device channels and using fusion models. On the right side, we visualize the confusion matrix of different models. The left table shows the results on the reduced gesture set, which means our sensing pipeline achieved a high usable accuracy for signature VAHF gestures. The right table shows the ablation of pre-training, dropouts, and the warm-up schemes have specific levels of negative effects on the performance. Here is the demo. For example, if the user wants to know how to make egg fried rice, they can perform different VAHF gestures to redirect their voice input to different targets, such as asking Siri, searching on Google, and sending a voice message to mom. The video shows the real-time recognition results.
Make egg fried rice. How to 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 make egg fried rice.
Thank you for your watching. Please refer to our paper for more details.